Hey everyone, today we're on Unit 5, Lesson 1, Polynomial Functions. So we're going to study polynomial functions this year again. You studied it in your Algebra 2 course. So we're going to move through this lesson rather quickly with the idea that you understand a lot of the concepts we're going to be talking about. First and foremost, identifying a polynomial function. A polynomial is a function in the form f of x equals a sub n x to the n plus blah, 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 a sub 0. This is very, very confusing. Okay, when we want to identify a polynomial, just remember, all coefficients must be real numbers and all exponents must be, this is important here, positive whole numbers. Okay, so a sub n. Okay, this guy out front here, the guy in front of the highest power, is called the lead coefficient. I will probably abbreviate it with LC, lead coefficient. N, okay, again, N is going to be the highest power. N is the degree of the function. Okay, it's the highest power in the polynomial. And also, it's going to be the maximum number of zeros we can find. And if you remember correctly, a 0 is going to be an x-intercept, and we'll talk about that more later on in the lesson. And so n minus 1 is going to be the maximum number of turning points. So for instance, if you have x cubed is your polynomial, okay, it's a degree 3, that means it can have 2 turning points. 4 can have 3 turning points. They can have less, but they can't have more. When we talk about polynomials, we want to talk about the difference between the standard form and the factored form. Now, the standard form is when we have no parentheses. So we're going to have everything as terms, and they're separated by pluses and minuses. So this would be a term. This would be a term, etc. Okay. The term and standard form also goes from highest power to lowest power. Okay. So this guy out here, the 2x cubed, that's going to be our term with our highest power. So in this particular situation, the lead coefficient, the number out in front, is 2, and the degree of this polynomial is 3. So in your head, you could think, oh, it can have 3 zeros. Okay. So when we're looking at the standard form, we identify the lead coefficient as the number in front, and the degree is going to be the highest power. When our function is given it to us in factored form, rather than foiling it all out and distributing, in order to find the lead coefficient and the degree of the function, you can just kind of look and see, are there any numbers in front of anything? In this case, no. So our lead coefficient is 1. And then to find the degree, that x really has a 1 as its power. This factor has a 1 as its power. And this last factor has a 3 as its power. So you would add up the powers of each factor. So in this case, our degree is 5. So what we're going to do in our first little set of examples is we just want to circle all the polynomial functions. And then for each one that's a polynomial, we're going to state the form it's in, the lead coefficient, and the degree. So as I look through, is 1 a polynomial? In front, I have all real numbers. All my powers are whole numbers, positive whole numbers. So yes, this is a polynomial. Our function is in standard form. So our highest power is the degree. And the number in front of the highest power is our lead coefficient. In example 2, this is also a polynomial. This form, though, is factored. It's in factored form. So in order to get the degree of the function, we would add up the powers of each factor. And then the lead coefficient, you do have to do a little bit of work here. Okay, so you do have to do a little bit of work. And there's a 1 here and a 1 here. So if I was to multiply that out, the lead coefficient is still a 1. In example 3, when I look at my powers, I notice right away my numbers are okay, but my powers, right here is my issue. I have a -1, so this is not a polynomial. In example 4 is good. Example 4 is in standard form. The highest power is 4, so the degree is 4, and the lead coefficient is 3/5. In example 5, this is also a polynomial. It's in standard form. This happens to be a line, which is fine. Okay, a line is a polynomial. Polynomial just means more than one term. Our degree is 1, so it's linear, so to speak, and our lead coefficient is -5. And in the last example, that's okay, but this is a problem. I can't have a variable as a power. This is an x, so this is not a polynomial. Okay? So we wouldn't worry about it. Now, once we know we're dealing with a polynomial, they're very special to us because the graph of every polynomial is smooth and continuous. Okay, it will have no sharp corners, no cusps, no gaps, no holes. So a polynomial is always going to be this kind of wavy, nice graph. In this course, it's important that you're able to just identify a graph as a polynomial or not. So as we go through these, in example A, okay, I always think, can you trace it without lifting up your pencil? If I trace this, I have to lift up my pencil to get to the next piece. So this is not a polynomial. If I'm tracing along this curve, this one's nice and smooth. So this is a polynomial. Over here, I have a corner. It's continuous, but it's not smooth. Okay, so we've got an issue here and an issue here. Not a polynomial. And in our last picture, this is smooth and continuous. So this is a polynomial. Okay, we included the words there just so you could see sort of how to identify when something is not a polynomial. Today, we're also going to just do a very, very basic look at finding zeros. I want to remind you that zeros are our x-intercepts. It's just a different word we use. So basically, x-intercepts are our solutions or our roots, so to speak. So you guys, all these words mean the same thing. Now, to find our zeros, we're going to set the function equal to 0 and solve for x. When solving for x, we have to use a number of different types of algebraic methods. So today, we're going to stay nice and basic. Everything is going to be something we can factor. So for instance, if I'm going to find the zeros here, I'm going to take our function, set it equal to 0, and then I'm going to factor it x minus 5 and x plus 1. If we set each factor equal to 0, like you've done in your previous classes, we get x equals 0, x equals 5, and x equals -1. Okay, so our zeros are x equals 0, x equals 5, and x equals -1. This leads to a very important theorem, and again, something you've talked about in previous classes. If r is a 0, or an x-intercept, so to speak, then x minus r is a factor. So if I give you zeros, you can work backwards and find that polynomial, which is what we're going to do in this example. So if I list your zeros as -3, 2, and 5, this means I can write a function. And if I take the root 0 and make it into a factor, it's going to be x minus -3, which is x plus 3. So when r is an x-intercept, x minus r is the factor. X minus 2 is another factor, and x minus 5 is another factor. And if we wanted to write this in standard form, we would FOIL this out. So I would have x squared minus 2x plus 3x is x minus 6. And I'm going to multiply that by x minus 5. X cubed plus x squared. Oh, I'm doing this opposite of how I usually do it, sorry. Minus 5x squared minus 5x plus 30. All I did was distribute. And again, that's something you know from Algebra 2. Combine like terms, x squared minus 5x squared. That's going to be minus 4x squared. Negative 6x minus 5x gives me negative 11x. And then I have plus 30 at the end. So something you should be able to do would be to start with a list of zeros, turn each into a factor, and distribute it out and get the function in standard form. Factored form, standard form. Just a little side note here. What's the degree of this function? The degree of this function is 3, right? That's our highest power. And how many zeros do we have? If we go over to our list, we have 3 zeros. So the correlation is there. The degree of the function is the number of zeros you have. Now let's kind of take a step back and think about what we did last unit. If I ask you to graph the following functions using transformation, let's think about what this basic function is. This basic function is x squared, right? So if I have my x squared function, and notice, I'm just visualizing it. I'm not making a perfect picture. And I'm doing what with this? I'm shifting it 1 unit to the right. So I'm taking and sketching x minus 1 squared. I want to do the same thing for x minus 1 cubed. Again, I'm going to start with my parent function, my x cubed function, which is our little snaky guy. And I'm going to shift that 1 unit to the right. Not going to be perfect. Okay, I'm not judging it on perfectness here. We're going to kind of talk about some important definitions from this point. Okay. So the first definition we're going to talk about, and is something you discussed last year, is a term called multiplicity. Multiplicity is how many times x minus r, or even if it's just an x, occurs as a factor of that said polynomial function. If our function, if our multiplicity is an even power, or an even number, I'm sorry, if our multiplicity is an even number, our graph is going to bounce. Our graph is going to bounce at that x-intercept. Okay, so if we look back up here, x equals 1 is our x-intercept, and our graph bounces there. If our function, if our multiplicity is an odd power, so if our multiplicity is an odd power, our graph is going to cross or cut through, however you want to describe it. Okay, at that x-intercept, again, here, x minus 1 is our factor, but x equals 1 is our x-intercept. So multiplicity, its definition is how many times it occurs as a factor. But basically what multiplicity does is it tells us what the graph does at a 0. Even multiplicity bounces, odd multiplicity crosses or cuts through. We have just one more little side note to make here. If the multiplicity is 1, or if the factor occurs one time, it's going to cross straight through. I can't spell. And if it's 3 or more, so if it's an odd number, 3, 5, 7, 9, whatever the case may be, it's going to flatten out and then cross through. So an example of that would be something that kind of goes like this. Right? So in this example here, it sort of flattens out. You're not going to see it. It's going to flatten out and cross through versus crossing straight through, which we'll see in later examples. Okay, so in this course, when we're talking about zeros and their multiplicity, I like you guys to use what we call a zero multiplicity chart. So we're going to go back up top here, and we're going to make a zero multiplicity chart for each of these examples. Okay. So in the 0 column, you put the actual x-intercept, and in the multiplicity column, you put the power, how many times that factor occurs. And then sometimes I may even have you describe in words what happens at each 0. In the second example here, 0 multiplicity. My 0 is 1, but this time my multiplicity is 3. So we're going to cut through. Okay. You don't have to do flatten out. You could just say cut. That's okay. All right. So we discussed multiplicity a little bit. And again, that's a term that should be familiar to you from last year. One last thing we want to kind of talk about before we graph one of these by hand is something called end behavior. End behavior is a little tricky to understand, but we're going to discuss it enough this year that by the end of the year, you'll be good at it. So end behavior is what happens to the y value when you plug in a really big X or a really small x. So in other words, in math symbols, it's kind of easier to understand. What happens as I plug in really big numbers or really small numbers? So end behavior is describing like the outside arms of the graph. Just going to go back up here for a moment. Let's look at a polynomial function. A polynomial function is either going to be like above or below. And you see, like my arms kind of go like this, but then I got a lot of stuff going on in between. Okay. So when we're dealing with end behavior, we're just concerned about our ends, what's going on there. We're going to describe right end behavior as x goes to positive infinity, what's happening to the right. Left end behavior as x goes to negative infinity, towards the left. And basically, there's 4 possibilities. Okay. When our function has an even degree, for instance, if we look up here, x squared is an even degree. Our arms, our right and left, are going to stay together. So even functions, x squared, x to the 4th, x to the 6th, are either going to both open up or both open down. Whatever happens in between, we don't care. Up, or both down. So evens stay together. If our lead coefficient is positive, our graph is going to open up like an x squared. Think of it just like an x squared. If it's an even degree and a is negative, Well, what's going to happen? We're going to flip it over the x-axis, and it's going to be down. So to get a little bit more detailed, as x goes to infinity, our function f of x also goes to infinity. Okay, now we're going to get a little more detailed with how we explain things. And as x goes to negative infinity, our graph is also going to positive infinity. Even degree with a lead coefficient, or a value. Okay, I should actually, a is the same as the lead coefficient. I should have mentioned that, I'm sorry. So as x goes to infinity here, as I plug in big numbers of x, now my graph is going to negative infinity. And the same is happening in the opposite direction. Now our odd functions are going to typically follow, so our even functions follow our x squared, and our odd functions follow our x cubed, odd degree. Doesn't matter the 3, 5, 7, whatever it is, as long as it's an odd degree, the end behavior will be the same. So in an odd function, in its most basic form, right, our end behavior behaves like this. So the way I remember is it even always stays together, and odd, they go in opposite directions. If a is positive, it's going to be the x cubed function in its most basic form. We don't care what happens in between here. And when our lead coefficient is negative, it's going to think about it, flip, just flips over the x-axis, so it's going to go there. If I ask you to describe it, as x goes to infinity, f of x, our function, goes to infinity. And as x goes to negative infinity, our function goes to negative infinity. In the last example, right, as x goes to positive infinity, f of x goes to negative infinity. And as x goes to negative infinity, the graph is going to positive. So I may, ask you to do a simple chart, or I may ask you to describe it with infinities. Okay, so just be aware of that. And the last thing we're going to do today is we're going to kind of put this all together so we could sort of visualize things. So if I give you a function in factored form, we can put all this information together and sketch a graph of it. It's not going to be perfect, but we can get an idea of what this picture looks like. So we start with the degree of the function. It's in factored form, so I have to add up the powers. 2 plus 2 is 4, so my degree is going to be 4. My lead coefficient is 2. My end behavior, as x goes to infinity, all right, I can't do it in my head, so I usually make a little chart for myself. The degree is even, lead coefficient is positive. There's my little helpful chart. As x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to infinity. Now we want to make a zero multiplicity chart. So we have to start with our original function and set it equal to 0. Notice I'm not dividing by the 2, I just don't care about it because I'm not going to get an answer there. There's no x. So I set this guy equal to 0. Now this is a tricky one because x equals 1, but how many times does that factor occur? Twice. And in the second term, or the second factor, x is negative 2, but also that factor occurs twice. So my graph is going to bounce and bounce at each of these x-intercepts. And the last thing that we could talk about is the y-intercept. And we know the y-intercept is what we get when we plug in 0 for x, 2, negative 1 squared is 1, 2 squared is 4. So our y-intercept here is going to be 8. Sometimes our y-intercept is not going to fit on our graph, and we're not going to worry about it. These are sketches. They're not going to be perfect. So instead of plugging it into y equals and getting a table of values, we're going to graph it from using this information. So basically, maybe what do I want to put on first? I'm going to put on my zeros. So I have a 0 at 1, and a 0 at -2. Now at these zeros, my graph is going to go up and up. And then my graph is going to also pass through 0, 8. Now, at this 0, my graph is going to bounce, so it's going to turn around at each 0. So if I'm thinking about what's going to happen in between, think about this. Your graph is going to go up and then come down again until you get to the next 0. And that's what your picture looks like. 0, 0. The graph is kind of turning at each of them. End behavior. And then how do I get from one 0 to the other? Good thing is you can always kind of check your picture with your calculator to make sure you did it correctly. Let's try one more before we end today. Our degree. So my x occurs once, that factor occurs once, that factor occurs once. So my degree is 3. My lead coefficient, the number out in front, is -1. My end behavior here, my degree is odd and my lead coefficient is negative. So my end behavior goes like that. As x goes to infinity, f of x goes to -infinity. As x goes to -infinity, f of x goes to +infinity. My zeros and multiplicity, I'm going to start with my original function, set each factor equal to 0. So -x equals to 0 is just x equals 0, x equals -2, and x equals 3. Each factor, so 0 has a multiplicity of 1. -2 has a multiplicity of 1. It's how many times that factor occurs. And 3 has a multiplicity of 1. So at each of these x-intercepts, my graph is crossing or cutting, however you want to describe it. And my y-intercept is going to be what I get when I plug in 0, -0, 0 plus 2, 0 minus 3. I didn't even have to go any further than this 0 because 0 times anything is 0. So I have an x-intercept and a y-intercept at 0. 0, 0. I have an x-intercept at -2. And I have a next x-intercept at 3. My graph at my end zeros, at the very last, so I go to the left. From my leftmost 0, my graph is going to go up. From my rightmost 0, my graph is going to go down. And then what's going to happen in between? Well, at -2, I'm going to cut through. At 0, I'm going to cut through. And at 3, I'm going to cut through. So if you think about it, this graph, before I draw the picture, is going to kind of start way up here. But as I travel down, I'm going to cut through. I have to turn around because I have to make it back up to this one. Then I'm going to go through. I have to turn around somewhere because I have to make it back to this x-intercept and then go down forever. And that's how we connect our x-intercepts, okay? So you always just kind of want to think about things before you finish up your picture. Is it perfect? No. Do we know where our turning points are? Absolutely not. We don't have those skills yet. We're not going to worry about them. Okay. What we're going to focus on is our degree, our lead coefficient, understanding the end behavior, and understanding what to do at each x-intercept, okay? So practice with your homework tonight, and we will see you very soon.